My name is Reza Olfati Saber. I'm an assistant professor of engineering at Tayer. I would like to welcome you to the first Complex Systems Symposium at Tayer. This is the third symposium in a sequence of three symposia that focus on the new directions of research at the Tayer School. And the first symposium was held 2 years ago and was called energy. That's the first area of focus. The second area of focus is applications of engineering in medicine, and that symposium was held last year. And the third area of focus is complex systems, which is this current symposium. So they would actually happen in a sequence. There would be 3 years from now, there would be the second complex systems symposium held here. The names energy, medicine, and engineering are very familiar to most people. And the one thing about complex systems is that you can't quickly or easily define it, and people have different perceptions or notions of what a complex system or a complex engineering system is or means. I remember that we had a committee meeting to talk about complex systems, and there were 5 or 6 of us. And at the end, we came up with 5 or 6 different definitions of complex systems. If you do a search on the internet, you would come across 2 most common meanings of complex system. One is the one that is more popular in the math and physics departments, and the term really originated in such departments or such fields. The focus of complex system or a study of complex system in those fields is to study chaotic behavior and chaotic systems. That does not happen to be the focus of our research or our program at Tayer. We are interested in design, analysis, and exploration of large-scale engineering systems that involve interactions of many components. The components or agents could be human agents or humans. They could be physical systems. They could be sensors and actuators, examples of physical systems. They could be software agents, and usually there could be some sort of extensive networks and computation and other components involved in the system. The best way to get a sense of what a complex engineering system is to just give you an example. For example, a futuristic type intelligent transportation system is a good example of a complex engineering system. Think of a transportation system in which cars have additional sensory communication and computational devices which allows each car to communicate with its neighboring cars or neighboring intelligent cars. I usually call them iCars, just I'm a big fan of iPhones, so that goes with it. So think of these cars as the main physical component with a lot of sensors and computational and communication elements on them. The main objective is to avoid collision between cars. So we're trying to, let's say, design a transportation system that would be safer than the existing systems. It's able to detect the pedestrians, it's able to detect other neighboring cars, trucks, and so on. This would be a way to reduce fatalities and accidents, and you could actually use such a system to also reduce traffic and as a result reduce pollution in an environment. So having lived in LA and gone through those 2 or 3 hours of being in traffic for 2 or 3 hours for a distance that would take at most 15 minutes to drive on a Sunday, I know firsthand how annoying it is and how much it actually wastes your time to be stuck in traffic. Most big cities, both in America and all over the world, have such traffic problems. So intelligent transportation systems could actually alleviate most of these traffic-related cost and waste of time, energy, and fuel and money. Another way that you could use such an intelligent transportation system is to view each one of the cars as an individual sensors that is gathering information about the city and traffic for you as a probe. So you actually could put additional gas sensors on, gas detection sensors or chemical sensors on top of your vehicle and basically record the amount of particles and other various types of chemicals and gases in an environment and get a clear sense of the pollution in a city. The same way the cars could actually count how many other cars, intelligent cars, are around them. As a result, you get a very accurate estimation of traffic in large cities. Currently, there are companies that provide you an estimate of traffic, but it's purely based on counting how many cell phones are active in a particular road and not how many cars. And they assume that just about everyone has a cell phone. So, and that's a good first estimate on traffic. So one of the main issues that arise from design of such complex systems that involve humans, physical systems, and cyber systems is that people might not be willing to reveal too much information, personal information about their car or their motions. One of the things that you could actually do with such a system, that the cars that actually have additional sensors, is that you could quickly detect drunk drivers or distracted drivers. So if the police has direct access to this information, and you have GPS location of the car, you just go for the target. So if there is a drunk driver, you could immediately identify the person and go right there and arrest the person. So many people would be kind of scared to drive if they've had any drink or they make the slightest mistake or something like that. So they're not willing to share this information with the police. So these are the social and policy aspect and mostly privacy aspects of such engineering systems. And that's why in our first session we try to have more experts and that specialize in privacy and sociology, and in the future we actually have to have more experts that specialize in psychology and political science and basically coming up with policies for making such systems more usable for a community. So I'm almost out of time. I'd like to take this opportunity to introduce our first speaker. It gives me great pleasure to introduce Duncan Watts. Dr. Watts comes to us from Yahoo Research. He's the principal research scientist at Yahoo and the head of the Human Social Dynamics Group. He's also an adjunct senior research fellow at Columbia University and an external faculty member of the Santa Fe Institute in New Mexico. He's one of the pioneers of social network research, and really needs very little introduction on that topic. I know from my own colleagues that both I teach some of his papers in my classes, as well as tens of other faculty members in my field who actually teach his work in their respective classes, regardless of the field of expertise, anywhere from computer science, various fields of engineering, to social sciences and psychology. So his papers, is not surprising, that has appeared in Nature, Science, Physical Review letters, as well as American Journal of Sociology. He's the author of 2 books, 6 Degrees, 2003, Norton, and Small Words, 1999, Princeton University Press. He holds a Bachelor of Science in Physics from University of New South Wales in Sydney, Australia, and a PhD degree in Theoretical and Applied Mathematics from Cornell University. Without further ado, please.
Does the clicker work? Okay. Thanks very much, Reza, and thanks for coming out on an early Friday morning. So today I want to talk really sort of exclusively about problems in social science, which is the sort of thing that I've been interested in for several years now, having moved over to a sociology department about 10 years ago, and working now in Yahoo, trying to sort of understand the hundreds of millions of people online and what they're doing and why they're doing it. And for those of you who are not familiar with sociology, I'm sympathetic to you. I didn't know much about sociology myself when I started teaching it, and it's an interesting question, like, what is sociology? And people ask me this all the time, and it's another one of these things like complex systems, where if you ask 10 sociologists what sociology is, you'll probably get 11 or 12 different answers. But roughly speaking, I think we could say that what makes a phenomenon social, as opposed to something about just an individual or psychological, is that it sort of critically comes out of the interactions of many people. So you take a bunch of individuals and you let them interact with each other, and somehow they create things that are more than just a bunch of individuals. So families, firms, markets, cultures, societies. These are entities that have their own, that are distinguishable in themselves. They have their own sorts of rules that govern them. But these rules are not reducible to the attributes of the individuals who make them up. And we just, in the same way that the cells in your body can all turn over and you still remain you, firms can turn over the individuals who work in them and still maintain their own character and culture and practices and so on. And so there's sort of the deep question of sociology really is how you get from this micro level of individuals interacting with each other and trying to sort of get through their lives to this macro level of the social world that we recognize. And historically, this has not been something that's really been possible. And you see this reflected in the disciplines of social science. You have microeconomics and you have macroeconomics. And one of the great challenges of economics that has sort of been exposed in the last year or so from a theoretical perspective is how you actually link the micro level of individuals to the macro level of markets. In the rest of the social sciences, you have psychology on the one hand, you have sociology on the other hand. They've never really been sort of successfully joined, even though it seems obvious that they should be. And I think the reason is that getting from the micro to the macro, and this is the reason why people are so interested in social networks and networks in general, is that somehow this aggregation, this emergence that we're interested in, comes out of these networks that are propagating information and influence, and these networks sort of exist in this kind of meso layer that's neither individual. You know, your network of people isn't you, but it's also not sort of the whole world either, right? So why are networks so hard to study? Well, two big reasons. One, they're extremely hard to measure, that they're essentially unobservable. The social networks that you carry around with you in your life are really sort of in your head. And even then, it's not clear that you necessarily know who all your friends are or know who influences you. You might think you do, but you might be surprised at you know, how you get your information and what you respond to and how you respond to it. And certainly doing this at very large scale has, you know, been historically impossible. That the, you know, the traditional way of doing social network research is you go out with a survey tool and you ask people, you know, who are your friends, who do you respect, who do you go to for advice, and these are just sort of very manual tasks that take up a lot of researchers' time, and so the limits on that tend to be, you know, of the order of a couple of hundred people. The other thing you can't do is experiments, unless you're sort of right, at least not controlled experiments. People, societies conduct experiments on themselves all the time, but not usually of the controlled or desirable kind. And so it's just very difficult. If you think about what science is, you know, you think about the scientific method that you learn in high school, it's essentially you have theories, you gather data, and you do experiments. And if you can't do 2 out of the 3 of those things, then you're in trouble. So what's interesting about the last decade or so is not just this sort of explosion of theoretical work in network theory and the ability of this, you know, the massively increased speed of computers that we have available to us now that allow us to sort of crunch through lots of simulations that we would have had to have worked out with a pencil and paper previously, but just the massive amount of data that is being collected. And the data is becoming massive. And so this is something that we sort of see every day at Yahoo, something like half a petabyte a year. I mean, we didn't even talk about petabytes until a couple of years ago. I mean, people didn't need that word, right? You know, a gigabyte was huge, and now we're sort of 1 billion times bigger than that. So, and the mail archives that we keep track of are sort of in the tens of petabytes already. So, so there's a tremendous amount of work going on in this field as this sort of ocean of data descends upon us. But today, I mean, there's, you know, a tremendous amount of interesting work going on in terms of studying very large-scale networks. And just to give you an example, Yuri Leskovets and Eric Horvitz at Microsoft Research published a paper about 1.5 years ago where they studied the network of Microsoft Instant Messenger users, which is 180 million individuals all over the world. So, you know, when I was in graduate school in the late 1990s, one of the first networks that we ever looked at was the network of movie actors, which had a couple of 100,000 people in it, and we thought that was enormous. You know, that seemed like a staggeringly large number of people to be sort of mapping out in a network, and within a decade, it's now 1,000 times larger than that. So very, very large scale, very interesting studies here. But what I want to talk about today is another sort of thing that the web has facilitated, another kind of work that the web has facilitated, which is doing experiments and sort of using the web as a virtual laboratory to try to understand what's going on in social interactions. You know, lab experiments, of course, have a very long history in the social behavioral sciences, mostly in psychology, but for, you know, at least 2 or 3 decades now, also in economics. And the reason why you want to do experiments as opposed to just observing things going on in the world is that it's much easier to understand causality, which tends to be what we really care about. Because we can actually control allocate people randomly to different conditions. We can vary the conditions very carefully. We can actually try to see what causes what. The downside of that is that these experiments tend to be kind of artificial necessarily. And so it's often difficult to generalize your understanding of what's happening in the lab to things that might be happening in the real world. And more relevant to today, it's essentially impossible to study large numbers of people in the lab. And it's something I'll talk about in a little bit. We ran, several years ago, we ran a series of experiments that involved almost 30,000 people, which is, how many students does Dartmouth have? Like a few thousand? So sort of the standard practice of psychology researchers over the years of recruiting undergraduates from campus wouldn't work on Dartmouth if you needed sort of several times the population of the campus to participate in a single experiment. You'd also never get NSF money to fund it. So the result is that we don't really have a field called experimental macro-sociology. And that's probably why you've never heard of that phrase. And I want to suggest that something like that might be able to exist in the near future if only we can build it using the web. And the way I'm going to talk about that is somewhat autobiographical, really just giving you a flavor of the sorts of things that at least people in my research group have been doing over the last several years. Going back to an experiment we did back in 2001 that sort of got us thinking about all of this, right up until literally the present. The last slide results I will show you were given to me by my postdoc, Sid Suri, yesterday afternoon at about 4 o'clock as I was walking out the door. So, and he's chained to his desk right now, generating yet more. Very current work, and actually very germane to the subtitle of this conference of Engineering Cooperative Networks, and we'll see why that is. So each one of these experiments is just something that we got interested in because we had some question that we wanted to answer, some sort of theoretical question. But along the way, we've learned things about doing experiments on the web. I'll sort of finish by, and maybe even leave it to the panel discussion to sort of do the hand-waving about what we might look for in the future. So going back a number of years now, actually, if we go back all the way to my graduate school training, when I was in theoretical and applied mechanics at Cornell, what got me interested in social networks in the first place was this wonderful experiment that was done by Stanley Milgram and his graduate student Jeffrey Travers back in the 1960s, which he called the small world experiment. And the idea was to test this hypothesis that everybody's so familiar with now today, we don't even sort of realize that it was once a hypothesis, that everybody in the world was connected to everybody else in the world through some short chain of intermediaries. And Milgram was the first person to test this by giving a bunch of letters, about 300 letters, to people in Boston and Omaha, Nebraska, which I think Milgram figured was about as far from Boston as he could possibly imagine without leaving the United States. And I've been to Omaha, and I think he's right. Each one of these people was given a lot of information about the target person, more than enough to identify him uniquely. But the catch was they could only send it to him if they knew him on a first-name basis, and that being very unlikely, they had to send it to someone who they did know on a first-name basis, who they thought was closer to the target than they were. So that person would get the letter and the same set of instructions and send it to someone they knew who would get the letter and the same set of instructions. And this protocol generated these letter chains that percolated their way across the country and through society, and about 20% of them, 64 of them, reached the target. And the famous result that Milgram observed that was very surprising to people at the time. He asked people, he described the experiment to people, and he asked them how many steps they thought it would take, and people would say hundreds of steps. I mean, they really had no idea that the number would be so small, and it was around 6. Presumably that's where this phrase 6 degrees of separation comes from, although Milgram actually didn't coin that phrase. That was the playwright John Guare. So I had done some work on this in grad school from a theoretical perspective, building little simple mathematical models to try to understand how this might be possible. But once I arrived at Columbia in the sociology department, we decided we might actually try to test this experimentally, except this time we thought we would do it on the web using email instead of physical packets. And so the nice thing about doing it on the web is that it scales very well, right? And we had this very interesting experience where we built this website, which was really just replicating exactly the same protocol as Milgram's, but where anybody could sign up to send a message. And nobody was coming. It was one of these, it's the Field of Dreams School of Experimental Design. You build the experiment and hope that people come. And nobody came, which was very disappointing. And we were sitting around brainstorming one day how to get more attention for this, and I went back to my office, and I had an email from this nice lady from the New York Times who had gotten one of our messages and would like to write a story about it. And would that be okay? I mean, would that be okay? Does anybody ever say no? So we said, yes, that would be okay. And so she wrote a story about it, and about 2 weeks later, we had about 30,000 people in our experiment. So we learned some things about the media as well. And so in the end, we had about 18 targets around the world instead of Milgram's one, and 24,000 of these message chains passing through almost over 60,000 people in 166 countries. And I think there's 192 countries in the United Nations. So this is sort of getting close to the scale of the whole world. And you can see how this works. This is one of the targets was my old advisor, Steve Strogatz, who insisted on being a target. And as a way to humor him, I said that would be fine. And actually, he turned out to be the sort of rock star of the experiment. He got the lion's share of all the messages, which was interesting and unexpected. So here you can see up in the top left-hand corner, just got a laser pointer on it. No. So in the top left-hand corner, those purple dots all show the original locations of the chains. They were all trying to reach Strogatz, who is the big red dot in the bottom right corner. And so you can see how they progress from step to step. And there's some interesting patterns about how they don't necessarily move linearly towards the target. Rather, they seem to, you can see over here, they coalesce in major cities, right? So there's a lot of people in New York, and then there's a bunch of dots on the West Coast in San Francisco and LA. And so this actually sort of supports Milgram's idea that Omaha is further from New York than San Francisco is. Socially, that's probably true. So this is really just a pretty picture to give you an idea of the global scale. But what was really striking to us about this there was some interesting science there. We've written some papers about it. But the point that was driven home to us that's relevant to the rest of the talk is that we really had this sort of epiphany that if we could just build something on the web that was somewhat interesting for people to participate in. There's millions of people around the world who are at work and they're bored. And they're sitting in front of their computers. And if you just give them something to do for 5 minutes, they'll do social science for you, right, for free. And so we thought, well, what else can we do? And so this is what led to another experiment a few years later that was joint with, I should say that my collaborators on that first one were Robi Mohammed, a graduate student at Columbia, and Peter Dodds, who is now teaching in the mathematics department at University of Vermont. And Peter also worked on this project with Matt Zalganic, who's now teaching in the sociology department at Princeton. And for a while, we'd been interested in this sort of interesting phenomenon in cultural markets for things like books and movies and music, which is that if you look at these markets, the distribution of success is incredibly skewed. So the biggest selling albums, like Michael Jackson's Thriller sold 50 million copies. The Titanic grossed $600 million at the US box office. The Harry Potter books sold 350 million copies around the world. So these are not just more successful on average, they're many orders of magnitude more successful on average. So if you look at the distribution of success in any of these markets, it's always very, very skewed. And you might suspect that the hits, the entities, the objects that are out in the tail of this distribution are sort of qualitatively different from the run-of-the-mill things. That if you and after the fact, that does seem to be the case. You certainly don't think about Thriller as just being a sort of average album. Unfortunately, nobody seems to be able to identify these hits before they happen. Right? So Harry Potter is a wonderful example of that. It was rejected by 7 now bitter children's book publishers before it was picked up by Bloomsbury, which at the time was a small independent press and is now a very large independent press. And you know, you have to think these guys are, you know, you have to sort of wonder, are these guys just lucky? And not just the people who pick the winners, but the winners themselves. And this is a very difficult argument to make. I mean, try explaining to some 12-year-old that, you know, Harry Potter is just like any other book, and it just, you know, people just bought it because other people bought it, and, you know, J.K. Rowling's just lucky, and you'll probably get kicked in the knees or something. And the thing is, you can't refute this argument that you know, the things that won because they were better, and we just didn't know it at the time, but now we do. And we know because they won, right? You know, markets are efficient, and so, you know, preferences are revealed. So the only way to sort of test which of these sort of stylized views of the world is true, the sort of, you know, things are just random versus everything works out the way it's supposed to, is if you can rerun the same process many times and see directly whether the same thing continues to win. So if you rerun history, you know, rewind history back to before anybody had heard of Madonna, and you run it forward another 100 times, and every single time Madonna ends up being famous, then you can say, well, listen, I don't get it. She's not my thing, but, you know, this is what people want, and so let them have it. But if you rerun history 100 times and Madonna is only famous in this version of history, and in every other version somebody else is famous and no one has heard of Madonna, then you would have to say that maybe she's just lucky. The problem is you can't actually do this, at least not in the real world, and so you have to set up an experiment. And again, the problem with the experiment is that if you want to set up, say, a market for music, which is what we want to do here, you need, you know, a large number of songs, and you need a large number of people to choose among those songs. So for one data point, essentially, you need hundreds of participants. If you want multiple data points, you need thousands of participants. If you want to have multiple experimental conditions, you need tens of thousands of participants, and that's too many undergraduates to put in a psych lab. So this is where the idea came of using the web, and this is an experiment that Matt built with our programmer Peter Housel called Music Lab, where people could come to this website and give us some information about themselves, and then they would come to this screen, which has on it 48 songs by bands that I guarantee you haven't heard of, and each grid square has a single band in all caps, the name of the song underneath it, and then you'll notice this little number over on the right-hand side is how many times the song has been downloaded by people before you. So you click on one of these grid squares, and the song starts streaming through your web browser, and you can give it a rating. And then, if you want to, you can download it, which is the thing that we pay attention to. And then it just sends you back to the main screen, and you can listen to as many songs as you want before finishing. What you don't know is that as you arrive, you're randomly assigned to one of two conditions. So the first condition is the one that you just saw, what we call the social information or social influence condition. And the other one is the independent condition. It looks exactly the same, except there's no numbers. Right? So you have to make your decisions completely on your own. Now, within this social information condition, we further split people into one of 8 different worlds. And what a world means is that you only get to see the downloads of the people in that particular world who were in front of you. So what we have effectively done is created 9 completely independent copies of the universe, all identical. They all start out with 0 downloads. And then we just run everything forward and we see what we see. I'm not going to go into any real detail about these experiments because I'm sort of trying to, it's really a whole talk on its own. As you can see, the total number of people, we ran 4 different experiments with 2 different populations. The first population was mostly high schoolers, teenagers who were recruited off a social website, a social networking site called Bolt.com that doesn't exist anymore, but was really sort of a teenage place. And the second population, we recruited by emailing all the people who participated in the Small World experiment a couple of years earlier and asking them if they would like to participate in another experiment. And these people were generally older, sort of average age in the mid to late 30s, and professionals. So sort of different populations and different conditions. In the condition I just showed you is what we call the weak condition, where everything's in a randomly scattered on a 6x8 grid. The strong condition is where all the information is the same, but we rank everything in a single list from most popular to least popular, so it's much more obvious which songs are winning. And that actually has quite an effect. And the final experiment was one where we actually tried to deceive people by inverting the rankings of the songs and making the best songs look like they were the least popular and vice versa. So there are lots of interesting results, and I'll just summarize them here. People are indeed influenced by the observations of others. It's quite striking. And the stronger the social signal, the more they're influenced. So that makes sense. What's less obvious and less intuitive is that at the collective level, this sort of emergent process that happens that generates the market, popular songs become, when people know what other people like, popular songs become much more popular and unpopular songs become less popular. But the particular songs that become the most popular become increasingly difficult to predict. And we can see that directly just by looking across the worlds. So the paradox of social influence here is that you're giving individuals more information, right? They're actually benefiting from knowing what other people think. This is helpful to people. I mean, it helps that we have, bestseller lists and critics and, ratings and all sorts of things because, otherwise we would have no idea what to even consider. But in giving individuals more information, the market actually aggregates less information because people stop paying attention to their own private information or stop trying to generate their own private information through experience and just trust the fact that other people have done the work for them. And so this is very sort of reminiscent of models of information cascades that have been studied in the economics literature. And really sort of raises some interesting questions about the idea of markets revealing preferences, rather than people having those stable exogenous preferences that the market sort of comes along and reveals. The market is actually constructing the preferences as it emerges, and so it generates this sort of fundamental ambiguity about where things are going. The other interesting thing that we found is that manipulating this is not such a manipulating this process is not such an easy thing to do. You can sort of you certainly can fool some of the people some of the time, but it turns out you can't fool all of them all of the time. And so there's sort of some interesting sort of complicated dynamics going on there, and you can read about that in a paper that came out last year in Social Psychology Quarterly. So moving right along, this is now work done at Yahoo Research with Sharad Goyal and Winter Mason, 2 of my team. And again, this is just a question that we got interested in because actually a former graduate student at Columbia, Dalia Baldassari, who teaches at Princeton now as well, wrote a dissertation that I read that was about polarization, political polarization in the US. And one of the sort of interesting kind of empirical mysteries that came out of this dissertation was that political sociologists and political scientists actually disagree about how much people disagree. There's been a lot of books and alarmist column op-ed pieces written the last couple of years about how Americans are sort of coalescing into these homogeneous, like-minded communities, and people are only talking to other people who agree with them, and so there's no political discourse across these partisan barriers, and this is a bad thing for society. But then other people have looked at the same, either the same data or done different studies of the same people, and found that Americans actually don't disagree with each other as much as people think, and friends disagree with each other much more than you might guess. And this disagreement can persist even in the sort of heat of an election campaign. And so it's sort of deeply unclear how much friends really agree with each other. And what might resolve this apparent disagreement in the empirical literature is that individuals in social networks simply think that they're much more similar to their friends than they really are. Now, this is a relatively straightforward hypothesis to test. The problem is testing it is difficult. And the reason why it's difficult is that to measure the difference between perceived and real similarity, you need to ask people questions, and you need to ask for a pair A and B who are friends, you need to ask what A thinks about this question Q, what B thinks about the question Q, and what A thinks B thinks about the question Q. And so you multiply this by lots of A, B pairs and lots of questions Q, and you have a lot of data that you have. Oh, Dartmouth conference today. Oh, that's helpful. So this is not difficult to do in principle. It's just very time-consuming and expensive if you want to do it with the standard interview-based survey methods. So right around this time, as luck would have it, Facebook launched their third-party app developer platform. And so we thought, well, this is, Facebook is sort of perfectly designed for this. The network is built in. It's a very large population. And we can just run effectively a network survey on top of this. So this is FriendSense. This is the app that Sharad and Winter built. This is Sharad. And this is my view of FriendSense. And you can see, so it's asking me, does Sharad Goyal approve of laws that deny US driver's licenses to illegal immigrants? This may sound like a boring question, but it's it's adapted from the general social survey. This is the kind of question that political scientists and sociologists ask people all the time. And so most of the questions that we used were off the GSS. And then we threw in some silly ones to try to make it a bit more fun. So Sharad's a pretty liberal guy, so I'm going to say, no, I don't think he approves of these laws. And then if it knows the answer, it'll tell me. And if it doesn't, it'll ask me if I want him to answer the question. And so I can keep doing this for as many, it just sort of throws up random people and questions until I get sick of playing. And some people got quite addicted to this and answered hundreds and hundreds of questions. And it is sort of a surprising sort of game to play. Up here on this bar is the 76% is the number of the fraction of questions that you get correct. Okay, so what did we find? We got about 1,500 people who participated, which is it's a very small number by Facebook standards, but not bad by survey standards. We have some profile information from them. We know, for example, how many mutual friends they have with each of the people that they answer questions about. And we have over 17,000 of these complete dyads where we know what each person thinks and we know what one of them thinks the other person thinks. And then we have all this other partial information as well. So this is sort of a fairly sort of large-scale study by the standards of things that you would try to do with an interview on an interview basis. And might cost you to put a module like this on the GSS would cost $200,000 or $300,000, which and take a couple of years. So this only took a couple of months and cost a couple of $1,000s on Facebook. So there's sort of there's all sorts of questions about sampling, and we can talk about that later. But from just a pure time and cost basis, it's a very interesting way of doing things. So what do we find? Just very briefly, this baseline homophily is one objection that comes up is like Facebook is not a representative sample of US society, right? We know that. It's true, by the way. Very, very liberal compared to US society. We don't actually care about the actual opinions. What we care about is similarity of people who are friends versus similarity of other people in the same population, right? So this is what we call baseline homophily, the probability that two people from our sample will agree about a particular question. And this is the homophily between friends, right? So that's the only thing that we're measuring here. And each one of these circles is a question. So what you're seeing here, because all these circles fall above the diagonal, friends are more similar than strangers. And that's what you'd expect. Good friends are more similar than casual acquaintances. So all these results are very sensible. Friends are also, by the way, think that they're more similar than they really are. So this is again, the observed homophily, and this is perceived. This is the answers that people give. And the reason why, the main reason why people think that they're more similar than they are is that they're extremely bad at telling when they disagree. Like they're so bad that they're worse than random guessing. Right? So on average, they only know about 40% of the time when they disagree with their friends. And this is true even when they're good friends, people who have lots and lots of mutual friends, who are embedded in sort of dense networks of mutual acquaintances, and when they say they talk about politics, right? And so when you talk about politics, you get a small boost, about 6 percentage points. But you're still under 50% for guessing correctly about disagreement. So, and it's even true for people who are minority opinion holders. So you might think that someone who is a staunch Republican teaching in an Ivy League sociology department would think that he was surrounded by a bunch of lily-livered liberals and would expect to disagree with them on most issues. But actually, those people are even worse at overestimating how similar they think their friends are to them than people who are in the majority. So it does sort of make you wonder this question, when people talk about politics, what are they talking about? They certainly don't seem to be talking about issues. And so this might have more general implications for questions of social influence, where we sort of just assume in our models that people know what other people think. But if actually all you're seeing is your own opinions reflected back at you, it's not quite clear how you're being influenced. So the final experiment that I want to talk about is the one that's going on right now, and is very. This is the one that's close to the topic of this conference, and maybe this is sort of the oldest question in social science, right? Why do people are selfish? Why do they cooperate? And they obviously do cooperate. They're obviously selfish. So there's this sort of tension here between very clear tendencies. And this is a question that Hobbes asked. Why is there not war of all against all? And social scientists and philosophers have been, and even biologists have been very interested in this question ever since. And Eleanor Ostrom actually just won the Nobel Prize in Economics for her work on studying cooperation in small-scale societies this year. So this is sort of, clearly an issue that people care about. And one of the sort of standard models, which is really the one that Eleanor has worked on, is known as what's called a public goods or public goods game or common pool resource game. And it's related to this idea of the tragedy of the commons that maybe you've heard about, where everybody gets some kind of endowment in this game. So we start out the game, I give everybody 10 points each, and then the game proceeds for some number of rounds. And on each round, you have a choice of how much of this endowment you want to put into the pot. So I can put in 0, or I can put in all 10 points. The pot is aggregated, it's multiplied by some constant, so let's say we'll double it. And then critically, the money or the points get redistributed equally back to all participants, no matter what you put in, right? So here's the dilemma. if everybody puts in the maximum amount every round, we all do very well, right? But individually, each of us does better if we put in nothing and everybody else puts in everything, right? So I want you all to contribute, and I want to stand back, right? But of course, you're thinking the same thing, and so we all stand back, so nobody puts anything in, and we all do badly, right? So this is where the dilemma comes in. And it's just a very sort of simple representation, a simple model of the sorts of problems that, that Ostrom has studied in the real world. As a result, these games have been studied very extensively in labs, particularly by Ernst Fehr in Zurich, and who's done many versions of this experiment. And you know, it has a number of interesting findings, which we'll see in a second. You know, one general observation is people tend to start out contributing high, and then over time they just contribute less and less. Players contribute more when they stay in the same group than when they get reshuffled to different groups each round. People, you know, if you sort of introduce people before the game and they shake hands, they tend to contribute more. They're more generous than they are if they contribute to strangers. So very sort of small priming, psychological priming factors matter. People like to punish, and punishment really works in terms of keeping up cooperations. But the point I want to emphasize here is that all these experiments have been done for groups of people, very small groups of people, usually 4 individuals, who sort of, what I mean by a group is everybody plays with everybody else in the group. In real life, it may be more complicated than that. It may be that you're sort of interacting with a certain group of people, and they're interacting with some of the people that you're interacting with, but they're also interacting with other people that you're not interacting with. And so indirectly, you can be affected by what these other people are doing. And this is really the essence of a network, and this is what really networks are, is that there's this sort of indirect effects that you might have to worry about. So the way that we're going to try to study this experimentally is by using this great website that I'm sure some of you have heard of, that is run by Amazon, called the Mechanical Turk. The original Mechanical Turk was a chess-playing automaton back in the early 19th century that was famous for having beaten Napoleon at chess. Now the Turk was actually not an automaton; it was a hoax. There was a human inside playing chess. And this is where the phrase artificial intelligence comes from, which is what Jeff Bezos uses to describe Mechanical Turk. So it was created as what we might call a crowdsourcing. Well, it's effectively what we call a crowdsourcing website, where people can throw up jobs, which they call human intelligence tasks, and the Turkers come and accept these jobs and get paid relatively small rates. So, you know, a classic job on Mechanical Turk would be tagging a photo, an image, you know, car, person, house, street, and then you can, and you might pay them 1 cent to do that. And so you can literally tag your entire photo collection of thousands and thousands of images for, you know, a couple of $100 overnight. So, which is much better than doing it yourself. So there's, you know, now thousands of these tasks any time of day on Amazon. It's quite an interesting phenomenon in itself. What we use it for really is just the equivalent of putting up signs around campus. We use it to recruit people to come to our experiments. The experiments run on our own servers on Yahoo's Research Sandbox machine, which you can take a look at if you go to the Yahoo Research website. We also use Mechanical Turk to pay them afterwards. So this is not free. This is different from Music Lab. It's different from the Small World experiment. It's real money, but it's cheap. The real challenge of this experiment is that we have to get people to show up and play at the same time. Oh, 2 minutes, okay, yeah. So this is the first thing we wanted to do actually was just check that you know, 10 years after Ernst Fehr's experiments in Zurich, using people who are living in a different country and playing online independently and not in a lab behave somewhat comparably to how they do in a lab. And actually, they behave indistinguishably from how they do in a lab. And this is actually sort of, I think, a remarkable result that the blue line is straight out of Fair and Gacta in 2000. And the green line is our replication of their experiment 10 years later. Theory would suggest that the larger the group, the less people cooperate, and in fact that's exactly what we see. So again, we're just sort of trying to sort of calibrate the system here. What we really want to do is understand whether network structure matters. And this is just a slide to suggest that we think that it should matter because there's lots of theoretical results that suggest that it should matter. Here's the test though. We take 4 different networks, a series of cliques, the cliques joined up in a cycle, the cliques with some random rewiring, and everything completely randomly rewired. So 4 very different network topologies with different path lengths and clustering coefficients and so on. Same number of nodes, same number of edges, just the links rearranged in different ways. What was surprising about the first round of experiments is that the level of cooperation doesn't seem to vary much across the different topologies. This was a big surprise to us. We really had the hypothesis that worlds in which your friends are playing with each other would be more friendly to cooperation than worlds in which your friends are not playing with each other. But it actually doesn't seem to make all that much difference. You just see this sort of, roughly speaking, people start out contributing half their endowment and they just sort of trend linearly downwards regardless of topology. So the experiments that we're doing right now is getting to this question of engineering cooperation. Can we actually shift these curves by getting in there and playing some of the players ourselves, right? So we now run a series of experiments where, so those ones we just let people do whatever they wanted to do. So now in each one of these 4 cliques, we pick one player and we play a dummy, right? And then we have 4 players in each one of these. And we now run 2 different versions of the experiment. One where the dummies play 10 the whole time. They contribute everything, right, the whole time. So they're very, very generous. And the other one in which they're very, very miserly. They contribute nothing the whole time. And we want to see how this intervention impacts the contribution of the remaining players. And this is mysterious. I don't understand this slide. This is the cliques over here. And you see when we play the dummies, you get higher cooperation. This is from everyone else, obviously not the dummies. Right? When we don't have any dummies, just the endogenous thing, then we get something in the middle. And then when we have the ungenerous dummies, it obviously, people get mad about it and they stop contributing. And they even sent us emails complaining that today the people were being really nasty. And yesterday they were really generous, and today is really nasty, and I'm confused. And so people are noticing. So this is sort of the intuitive, the obvious result that you might expect. The other 3 topologies have this very strange pattern where, for the cycle, the zero dummies are behaving in exactly the same way as no dummies. But the opposite is true for the other 2 topologies, where here the generous dummies are not really having any positive effect, but the non-generous dummies are having a negative effect. So there's this sort of strong asymmetry that you can either sort of make people be more generous, or you can make them be less generous, but they respond sort of asymmetrically to these different kinds of stimuli. So I think I'm out of time now, so I'll just sort of wrap up by saying, again, just sort of coming back to the methodological issue, that chart that I just showed you represents 53 experiments with 24 players in each of them, which we've run over the last 6 weeks, and now we're running about 4 a day. And overall, we've done about 133 cooperation experiments over the last few months. And the total cost is about $3,000. So this is an incredibly sort of flexible, fast, economical way of doing these experiments. And they do seem to generate results that are indistinguishable from doing them in a lab. So this is sort of something that we think has a lot of promise. And we're going to try to do bigger networks, different topologies, different kinds of intervention strategies, different kinds of information conditions, and maybe even different kinds of games. Okay. There's no sort of overall message here except that there's a progression of different experiments. They each have sort of strengths and weaknesses, very large, some are very large scale, but not controlled. Others are controlled and medium scale, but not really networked. Those most recent ones are really looking at networks, and they're really controlled, but the scale is still somewhat small. We really hope that you know, at least both at Yahoo and other places, we can really sort of start to tap the scale of the networks that we're talking about and do experiments in a somewhat sort of routine and controlled way on a routine basis. And we think that that may have some big implications for social science. Just going back to the original point that I made, that if you can't measure things and you can't do experiments, it's very hard to do science. When you suddenly turn around and you can do experiments and you can measure things, a whole lot of things that you couldn't even imagine measuring just a decade ago, you have to wonder where that is going. And so I'll stop now. Thanks very much.
Let's have a few quick questions, and you would definitely get a lot more time during the panel discussion to ask more questions. So, any questions?
With the little experience that I have, it seems like some of the experiments, if you were to do them in a university setting, you'd have to engage the IRB and so on. And so, I guess my question is, because you're at Yahoo, are you able to do stuff, for the cost and quickly without the overhead of IRB that the university people would have to engage?
The short answer is no. I mean, the first two experiments that I talked about were done in universities and did go through IRBs and all that sort of thing. And we have a review process that's something like an IRB. I mean, you can't just do anything you want. I mean, obviously, in fact, in some ways, corporations are even more sensitive about certain things than universities are, because there's a very sort of strong reputational risk. So yeah, this is sort of a brave new world for Yahoo and for other corporations. They're not used to this, doing sort of behavioral science, and so we've had to sort of educate people a little bit about what universities do and what practices we should import and what things we should streamline. But the basic answer is we have to sort of worry about exactly the same set of issues, and we do. Yep.
Just a quick question about the platform. So you're at Yahoo, but you experiment on Facebook and Amazon Mechanical Turk. I wonder, does Yahoo have a platform for this? You just think it's not dynamic enough, or Yahoo is planning something to actually use this?
Well, yeah. So we do actually have a platform. It's this thing here, the sandbox. And the Facebook one was an app that ran on Facebook servers. But the Mechanical Turk ones all run on our servers. It just sits in a frame on Mechanical Turk and then just hits our server in the background. So yeah, we are. But we may be great actually in the long run to have our own panel. And this is something that we're sort of talking about building up, to have a sort of own research, opt-in, population of people who like participating in our experiments, and we just, we can sample from them and contact them whenever we have an experiment to do, and we have our own payment system, and so that's something that we could do in the long run. But right now, it's just very sort of fast and convenient to do it through Mechanical Turk.
So you do the different experiments, different group of people again, or you do different experiments with the same group of people?
This most recent, over the course of these experiments, it's been different people, but for this most recent round of experiments, we started out with different people, and then we kind of got a stable population, about 100 people that we contact every time. So So most of these results are for the same group of people playing this game over and over again. And we sort of actually, it's an interesting question because you might worry that people become sort of professionals at playing this game and that they would play systematically differently, and they don't, which is interesting. Yeah.
This may be less interesting to this crowd, but it's a theoretical question about your results that you just got yesterday. So I know you haven't had a lot of time to think about it, but the networks have different implications about the reciprocity expectations of the other people in the group. So it seems like that, and I can't think through them for the random graphs, but for the cycle, right, it's a generalized, distributed reciprocity potentially that comes into play rather than just within the group.
Well, what's interesting is actually just, I don't mean to cut you off, but from an individual's perspective, all these things look exactly the same. Right, so you just see, there's you just get like a little graphic, and it's you in the middle, and then you have your 5 neighbors around you. And you can't see who they're connected to or whether they're connected to each other. You just see that information. So everybody has the same experience of the game. What's different is that in the cliques, there's only one, defector, for example, who you can be exposed to. But once you start connecting the different cliques, then you're talking to someone over here who's also getting raked over the coals by somebody down here, and so you can have these indirect effects propagating that you can't get in the clique. So I can certainly understand why the cliques would be different from the connected networks. It's just not clear why the connected networks are different from each other in the way that they are. But certainly we could do what you're suggesting and let people, and I bet that would change things. If people knew, for example, that their neighbors were talking to each other, they probably would behave differently, and that's something that we'll do in future work.
I really need to beat a dead horse. I'm going to do it anyway. What sort of ethical challenges do you face regarding individual privacy settings in your studies? And feel free to sort of defer from that question if it's outside of your domain of expertise.
Well, mechanical Turk again is very convenient in this respect, and that all we know about them is what they tell us, right? So we do ask them questions about their gender, age, income, whether they're playing this at work or at home. We know what state they're from, but that's the level of information that we have. That we store on our servers in a secure way, so it's not, we don't publish even individual level data at that of that nature. It's just aggregate statistics. But everything that's sort of sensitive, like their actual identity, their email address, their financial, their bank account, everything, Amazon handles all of that, right? So we can sort of.
Quick question.
Yeah.
I actually have a follow-up on the previous question from before
Yeah.
the study. And it's kind of the same question, maybe from a different point of view. Presumably you have a hypothesis about the propagation speed of this information through the different types of networks that you're setting up, between the sort of connected cycle versus a randomized version versus a totally random network.
Hypothesis would be too strong a word. Our hypothesis is it might matter, right? We don't.
Why did you pick these particular network topologies?
Well, okay. So I guess I can be a little more specific. Just some from previous work. It's both my own and going back to sort of work from Bob Axelrod and other people. There's this sort of general notion in cooperation games that that if cooperators preferentially interact with each other, they can sustain cooperation, right? Whereas when they are randomly paired, then cooperators get exploited by defectors, and so cooperation collapses. And so this is sort of a way to try to formalize that. So up here, you could imagine that these guys, if they start out cooperating, they're going to be able to kind of keep it up for longer than over here. If the same 6 people start out cooperating, they're going to be exposed to all these other people who are not cooperating, and so they're going to actually get undermined. Now, that's why it was interesting that didn't really happen in the endogenous experiments. We expected to see the blue line, which is the cliques, really sitting up above the light blue line, which is the totally random graph. And it's very surprising that there's no such effect there. So maybe they're not playing the same rule that we think they're playing, right? It's not clear what individual level rule is being played here. But something like that does seem to be happening once we start actually intervening in the network. So that's the reason why we wanted to. So the 2 things we're varying is this clustering coefficient, which is the probability that your neighbors are also neighbors of each other, which tests this sort of idea of preferential interaction. And the other is that the path length is varying. So in the rewild, in this cycle here, it's like people on average are 2.5 steps away from each other, whereas here they're only 2 steps away from each other. This is not a big difference, but it's the best we can do with these at this scale. So the idea there is that if things are spreading, they're going to have more, let's say, influence is decaying rapidly with distance. So that I influence people who are my neighbors and they influence their neighbors, but my effect is lost after 2 steps, right? So then we ought to see, more of an effect over here than over here, where here everybody is sort of getting affected by a single bad apple, for example. So we're trying to sort of vary the global connectivity and the local density to see if those things matter. But the problem is that you can sort of get any result that you want in simulations, depending on what assumptions you make about what strategies people are playing. And this is, in a way, the motivation for doing experiments, is because then we don't have to make up rules for what the people are doing. They just do whatever they do. And what they do seems to be rather simple. If I had to guess, I would look at these curves and say, the rule is start out contributing half, and then every period after that contribute, 1.9 of what you contributed last turn, right? And I wouldn't be surprised, actually, if what people thought they were doing is actually matching what they think their neighbors just contributed, but that they have a bias towards under-contributing. In the same way that when large groups of people split the check at dinner, nobody ever pays more than their fair share, right? It's like you're not trying to stiff your friends, but you're trying to actually pay exactly what you think you owe, right? It just so happens that you're more likely to underestimate than you are to overestimate, right? And so I think it's possible that something like that is happening here. And it's a very simple rule, but it seems to account for what's going on. And we have a lot of feedback from our players that we have to kind of, go through. But just sort of glancing at it, that's consistent with what we're seeing.